Hello everyone, myself Anushka Jadhav. Today I am going to present bending moment analysis of cantilever aircraft tail boom. So, bending moment analysis. So, it means understanding the forces that act upon a aircraft tail boom is a critical for flight safety and structural integrity. It means the forces act upon the aircraft of the tail boom. So, introduction. Why tail boom structure matters? So, the tail boom is a vital structural component of many aircraft for supporting the empennage. It is nothing but the tail assembly and often housing control surfaces or propulsion elements. So, its integrity is paramount for flight stability and control and any structural failures due to the undamaged bending movements. So here are some fundamentals of bending moment and cantilever beam. So first we have to know what is bending moment. So bending moment is a measure of internal forces causing a beam to bend. There are some examples like Newton's meter are crucial for predicting stress distribution and potential failure points. So that is the bending moment. So what is cantilever beam? So a cantilever beam means it is fixed at one end and free at other end. So it means a common configuration for aircraft tail booms. So here we can see some tail boom structures and operational loads, like a structural form is a semi-monocoque or a monocoque structure to optimize strain to weight ratio. Then there is aerodynamic loads like forces from airflow over control surfaces. Examples like radar, stabilizer, means elevator. Then inertial loads means weight of components like occupants and payloads within the boom itself contributes to bending movement. Then dynamic load means turbulence and landing impacts introduced due to the fluctuating. So let's talk about free body diagram and load idealization. So what is FBD? FBD means the diagram which can be drawn by freely, means there's no there's no fixed dimensions to draw. It is essential for isolation the tail boom for its surrounding and identify all external forces and movements acting upon it. Then load idealization, it means simplifying distributed loads, for example aerodynamic pressures into equivalent points loads or uniformly distributed loads. So here are some examples. Here is a step-by-step calculation for simplified. So define geometry. So we assume a 3-meter boom with uniform cross-section area. Then here we take the 5 kg of free end load and representing empennage weight. Then section. Then we take 1.5 meter of the section. Then after applying equation, we have to multiply the empennage weight and section, then we get 7 - 7.5 kilonewton meter. Then the result is the bending moment of 7.5 kilonewton meter is experienced at the section and indicating internal forces uh, resisting bending. So here we can see interpretation of bending moment diagrams. So maximum moment. So let's talk about interpretation of bending moment diagrams. So maximum moments. So maximum moment means the highest point on the BMD indicates the section experience the greatest bending stress. Then critical section, it means locations of maximum movement changes in geometry or material properties that requires extra attentions in design. Then inflection points, like where the bending moment changes sign indicates a change in curvature of the boom. So here are some applications of structural design. First is material selection. So choosing material with sufficient strength and fatigue resistance for critical areas. So it is the important point to choose the right material. Then life prediction, it means assessing how repeated load cycles will affected the boom's long term durability. Then component sizing, determine the appropriate thickness, cross sectional area, and weight. Then certification and compliances, like ensuring the designs meets the airworthiness and for the safety. So from this, I concluded that the compressive load understanding, like accurate identification and idealization of all the operational loads are paramount. Then critical section identification, like bending movement diagrams. Then there are vital tools. Then third point is informed design decisions. So analysis directly influences material choice. We have to choose the correct material. We have to choose the size, thickness, and cross-sectional area also. Then overall airworthiness for safety. Thank you.